Hi, I'm Bob Janzen with Palmer and our Mineral Exploration and Surficial Geology team. Today I'm talking about orphaned indicator mineral trains, and we're going to be solving old problems using a new perspective. This talk is largely focused on diamond exploration, but the methods described herein are applicable for all commodities. There are numerous orphaned indicator mineral dispersals that present new opportunity for kimberlite discoveries, but these orphan dispersals have eluded explorers. Within Lac de Gras, these might indicate individual or small clusters of undiscovered kimberlites, but outside of Lac de Gras, there could be new kimberlite districts waiting to be discovered. In this presentation, I'll discuss how advancements in data resolution and surficial exploration methods provide new insights into the evolution of these orphan indicator mineral dispersals, and they can lead to new discoveries. First, a little bit of information about Palmer. Our team provides and implements data-driven surficial exploration strategies for mineral exploration. We leverage our experience collaborating with government, industry, and academia to advance the application of quaternary science in mineral exploration. On the map shown here and illustrated in blue, we've interpreted surficial geology in over 15,000 square kilometers of the Slave Geological Province, and compared numerous data sets which provide us with an unparalleled understanding of the implications of surficial geology for mineral exploration. We've been able to apply successful strategies that focus on the evolution of a landscape and compare analytical results to identify the link between materials and the dispersal of indicator minerals. So why are orphaned indicator mineral dispersals relevant now? Well, investment in exploration for diamonds has diminished to its lowest level since the Great Recession. But nothing will change this trend more quickly than a new discovery and inject life and money back into the exploration for diamonds. However, this has become increasingly difficult during a global pandemic and with many travel restrictions in place. There is potential for new discoveries in Lac de Gras and beyond, but the area outside of Lac de Gras has largely been ignored. As shown by the active mineral leases and claims, most efforts are focused in Lac de Gras because investors feel safe putting money where previous discoveries have been made. Here, there are still a few orphaned kimberlite indicator mineral dispersals, but there are also numerous indicator mineral dispersals beyond this area that have not been explored in as much detail and could represent new diamond districts. On this map, the area circled in red represents the Lac de Gras kimberlite field. As you can see, the highly anomalous Lac de Gras area is taking the spotlight from peripheral areas that are also anomalous, as indicated by the areas shaded in orange and green, that are overlooked and underexplored, but also contain elevated kimberlite indicator mineral concentrations above background, which is black. We need a cost-effective approach to advance exploration programs, in many cases remotely, thanks to COVID, and ensure we hit the ground running with effective data collection. Today, I'll discuss why some orphan dispersals have eluded discovery by providing a brief description of key primary and secondary factors affecting dispersal patterns, provide some examples of desktop studies that can advance our understanding of these dispersals and their source regions, and how these desktop studies can be used to design streamlined, data-driven field programs to collect high-quality data, specifically where it's needed, that can lead to new discoveries. When indicator mineral expression occurs in the surficial environment, we all think of a gently rising plume of material from the source to the ground surface in the same direction as ice flow, as illustrated. This is the ideal dispersal. While ideal dispersal does occur, most dispersal is considerably more complicated. To unravel complicated and confusing patterns, we need to understand the evolution of the landscape. After all, these dispersals are literally embedded in the surficial materials, and therefore a comprehensive understanding of their evolution is an absolute necessity in identifying a source. Now, let's move on to some of the primary and secondary factors that control dispersal patterns. The deposition of indicator minerals initially occurs as a result of ice eroding mineralized material and depositing it in a down ice direction. However, many areas, including Lac de Gras, have been subject to multiple time-transgressive ice flows depositing material in many directions. The mineralization that does not align with the dominant ice flow is known as palimpsest dispersal, as illustrated. This is an example of ice flow controlling the direction and shape of primary dispersal. In this figure, the bottom section displays the initial ice flow to the east with a mineralized plume that rises from the source to the surface. During an ice flow reversal to the west, middle figure, we see that the mineralized plume continues to rise to the surface, but it continues from the previous surface expression of mineralization. At the top, we can see that the ice flow once again reverses to the east and the dispersal plume slightly shifts back toward the east at the ground surface. This thick till dispersal contains a profile with the surface samples showing the cumulative effect of multiple ice flow events. The drift thickness provides an expectation of short versus long transport and whether there may be more complexity in the thick sediments than is apparent at the surface. In a thin till, the plume of mineralization does not reflect the reversals within the till column like a thick till. Instead, the plume of mineralization reflects the most recent transport direction and completely erases the previous signature. These aren't the only factors. There is even more complexity when you start considering primary entrainment potential and re-entrainment, as well as many other factors that are beyond the scope of this discussion. Let's look at a real-world example of till thickness affecting dispersal patterns. The source of the famous copper-mine indicator train, west of Lac de Gras, has long been sought. The top figure displays the monument kimberlite indicator mineral train, with a known source, along the south shore of Lac de Gras. But there is an additional indicator train, the copper mine, that still has no known source, despite an abundance of indicator minerals in the superficial material. Speaking of the superficial material, the bottom figure shows that in this area, most of the superficial material is thin veneers to intermittent with bedrock exposures. This is the white to light blue. However, there are pockets of thicker material, the greens, yellows, and reds. Additionally, ice flow indicators are preserved in two main directions, to the southwest, but mainly to the northwest, which is the most recent regional ice flow movement, and it's also the reason the monument and copper mine indicator trains trend toward the northwest. The superficial material was investigated in 3 dimensions using drilling and sample collection. This image shows the borehole data stacked with each dot representing a 1.5 meter interval and the location of the borehole at the base of each column. The indicator minerals show that in the northwest direction, there is a plume of highly anomalous indicator minerals that rises to the surface, similar to our ideal dispersal. However, the variation in ice flow causes palimpsest dispersal as well. If we look at the samples to the southwest, we can see that there is a subtle indicator mineral signature preserved in the deeper sediments. The variation in drift thickness affects how the pattern manifests at surface. Understanding the drift thickness and ice flow history allows us to better interpret what we see and identify the best supported target, because in this instance, there is 2 dispersals with the same source. Now we can see that the till thickness affects dispersal and the materials that are preserved. But what about the superficial material itself? From Palmer's previous work, we understand how different processes affect kimberlite indicator mineral counts. On the left is a map view of the primary dispersal that points to the source. The darker shading represents higher indicator mineral counts. In the center, you can see how meltwater can remobilize and offset the primary dispersal, resulting in an increased concentration adjacent to the primary dispersal. On the right, we add one more complication of a glacial lake. It deposits largely barren material over top of the dispersal, which then cryoturbates into the till, resulting in a dilution of the primary dispersal. So how does that translate to our surface sampling results? Here, we see a series of dots representing kimberlite indicator mineral concentrations in the surface sediment samples. Most likely, an explorer would look up ice from the cluster of highly anomalous samples. However, they would be wrong. If, however, the explorer was armed with the knowledge of the meltwater and the glacial lake effects, they would unravel the evolution to identify the true source. So how do we identify where dispersal patterns have been affected by these post-depositional processes? If we look at the figure in the top right, we can see two images of the same location with a vast improvement in the visual resolution over the last 10 years. This increasing availability of high-resolution, remotely sensed data and advancements in software allows us to collect detailed descriptions of the landscape that were previously only achievable through expensive field programs. For example, in the 90s, one would go collect several samples in the field, come back, evaluate that data to find some unexplained pattern. The following year, they would go back into the field to try and explain any patterns, collect more data, then come back and look at it all again. High-resolution data allows us to do much of this from our desks. Palmer uses 3D mapping software to create products such as surficial maps right from our desks. This is a low investment opportunity to significantly advance exploration opportunities. Surficial mapping is the foundation to understanding the surficial environment, which provides the framework in which we interpret the dispersal patterns. This creates an inventory of materials. Is it till? Are we looking at primary dispersal? Is there enough unmodified till for till sampling to be effective? Or do we need to consider other strategies? The surficial maps also create an inventory of processes, such as post-depositional modification, to the dispersal that needs to be considered. One such modification is glacial meltwater that has a huge impact on the Northwest Territories landscape. In this example, we see till in green, glacial fluvial material in orange, and reworked or modified till in red. The meltwater has the effect of concentrating indicator minerals, and we can see that through the elevated average kimberlite indicator mineral counts, the box plots on top, and higher overall kimberlite indicator mineral counts, probability plots, on the bottom. This shows how understanding the material and processes allows us to tease out the primary dispersals and interpret results from non-till or modified till samples. The high-resolution surficial geology mapping provides a context for understanding existing sample genesis. We can't assume all samples called till are actually in situ till that provides a primary dispersal pattern. If we examine the existing Northwest Territories KID database on a regional map, which is the top figure, we can see that the archive data sets are not always what they seem. The majority of these samples are classified as till. However, the bottom map shows the same samples reclassified based on our surficial materials mapping. You can see a stark difference in the classification of the sample media, which is varied between modern processes, till it has been modified, and material that does not contain till at all, but rather it's glaciofluvial or glaciolacustrian material. This informs us that some samples are part of the primary dispersal, till, some have been modified or reworked, or even possibly remobilized and are part of a secondary dispersal, such as an esker. This provides us with the understanding of sediment transport history beyond ice flow, so that we can tease out primary and secondary components of the dispersal. Now, for the most important question, how do we use this information for data evaluation? One example is the mapping of the Coppermine area, which was completed for the NTGS and is publicly available. This shows that there's quite a bit of till, so sampling should work, but there are several glacial-fluvial corridors that may affect the distribution in surficial materials, and when we compare the existing data, we see that a number of the samples fall into polygons that are not identified as till, or post-secondary modification is expected. You can see northwest trending corridors where meltwater has affected the till. You can also notice areas of increased rock in red in the northwest where the till was removed by meltwater. So we can expect a paucity of indicators in the dispersal pattern. So what else can we provide with this surficial mapping? Well, we can create derivative products to inform field programs such as till sampling suitability maps. Northwest Territories is a big place, and dispersals cover large areas. Mapping and derivative products ensure fieldwork is optimized by targeting the right areas for specific tasks, such as till sampling sites or bedrock mapping. Sampling suitability mapping identifies where surface till sampling will work and where other exploration methods may be required, such as subsurface sampling, soil gas, or even microbes. Till sampling suitability mapping helps focus sample collection, generally related to till, because we want to find the primary dispersal. But it can be tailored for a specific environment. For example, if there's no till, it can highlight different glacial-fluvial landforms based on their suitability. This can streamline collection and ensure optimal distribution and quality data by planning on till sampling suitability. Till sampling suitability also provides advanced knowledge of where sampling will be easy and what areas are more complex and will require more time or a more experienced sampling crew. An example from the same area of the copper mine shows that the implications of surficial processes are reflected in the sampling suitability mapping. Although much of the area was green in the surficial map, which indicates till, you can see that there's more light green, yellow, and red, indicating a decreasing sampling suitability. If we were to design a field program based on the till sampling suitability, we would pick locations in dark green polygons to retrieve primary dispersal material. We would avoid the yellow and red polygons where post-depositional processes have remobilized or concentrated kimberlite indicator minerals, which would obscure primary dispersal and make it more difficult to identify a source. We can use this information to optimize sampling programs by recommending ideal sample locations to attain optimal sample distribution for the minimum number of samples while maximizing coverage. And this minimizes the effort and time to locate and collect only the appropriate sample material. This also ensures that the effect of post-depositional processes on the sample media is minimized, and therefore the data received is more indicative of the original indicator mineral concentrations. Surficial mapping also allows us to create drift thickness maps. These are an interpretation of relative drift thickness derived from surficial interpretations and informed by depth to bedrock data where available. This data informs interpretations on dispersal lengths and direction, as well as the cumulative effect of multiple ice flow events that we discussed earlier in this presentation. It also informs bedrock mapping initiatives and sampling methods such as where drill sampling is effective and where it is a waste of time and money. Starting a drilling campaign without prior drift thickness knowledge can get you into a situation where two holes need to be drilled side by side in order to get enough sample material because the drift is so thin. In areas like this, a shovel would be much more cost effective. By comparing the till sampling suitability and drift thickness, we can identify areas that are most favorable for subsurface, e.g. drill supported, sampling. One thing we haven't talked about today is how this affects target identification. This process improves data evaluations based on detailed surficial mapping. It provides genetic subpopulations with comparable analytical results only. The map in the top left shows the unprocessed kimberlite indicator mineral data from the KID database. The map on the bottom left shows the same data processed within the surficial context provided by the superficial mapping. This is an entire talk on its own, but we've all heard the apples to apples metaphor. In this case, we're talking about differences in both transport history due to remobilization from primary till dispersal and anomaly thresholds due to concentration or dilution of kimberlite indicator minerals by post-depositional processes. This is the unprocessed versus processed results. We need to ensure that apparent anomalies are not related to the concentration of heavy minerals by depositional processes. To really drive the point home, the figure on the right shows a proportional dot plot in till in glaciofluvial samples. We can see that the till generates dispersal to the west along the main ice flow vector. The glaciofluvial samples, however, follow along the meltwater corridor that trends toward the southwest. Anomalies in the glaciofluvial sediments are generally higher than in till. If we look at both of these results together, the glaciofluvial material will mask the till anomaly and will focus our efforts on the glaciofluvial units instead of the source of the primary till anomaly. To summarize this presentation, we note that investment in diamonds is down, so there's limited money and COVID is making field work near impossible. Many orphan dispersal patterns within and beyond Lac de Gras indicate a lot of potential discoveries. Areas beyond Lac de Gras are getting little to no attention right now, and desktop studies can significantly advance exploration on these orphaned indicator mineral dispersals, especially considering the increased availability of high-resolution data that provides near-ground observations with comparable data at a fraction of the cost of fieldwork and over much larger areas than you could visit in the field. Utilizing desktop studies during the winter and COVID restrictions advances our understanding of orphaned dispersals, indicates critical data gaps, improves data evaluations and targeting, and provides critical data to streamline expensive field programs and ensure quality data are collected when we can get our boots back on the ground. So if you're interested in a better way of targeting mineral deposits and making use of desktop studies that are almost as good as having boots on the ground for a fraction of the cost, please contact Palmer through Dave Sacco, our Senior Superficial Exploration Specialist, at 778-689-2721 or dave.sacco@pecg.ca, or myself, Bob Janzen. I'm a quaternary geologist here with Palmer. You can call me at 289-407-8360 or bob.jansen@pecg.ca. Thank you.